This map projection shows the standard commercial routing between the U.S. West Coast and Southeast Asian hubs, taking upwards of 15 hours. The Apollo-Mindanao trajectory replaces this with a Mach 20 ballistic arc, arriving in the Davao Gulf in 37 minutes. Executing this Earth-to-Earth transit relies entirely on a specific vehicle, SpaceX's Starship system. To compress a 15-hour flight into 37 minutes, Starship alters the spatial parameters of intercontinental travel. It targets an apogee of 125 kilometers, ascending past the Kármán line and into low Earth suborbital space. Conventional airport infrastructure is useless for a flight profile like this. Reaching that apogee requires a strictly offshore-to-offshore launch and landing model. Shifting operations to the ocean is only the first hurdle. Executing this timeline requires solving major physiological bottlenecks for civilian passengers who will be subjected to extreme acceleration and deceleration. And then there is the financial reality. The astronomical volume of cryogenic propellant required to reach suborbital space mandates a high-yield economic model to make the route commercially viable. To deconstruct how these systems integrate, we can track the exact 45-minute operational timeline, ranging from pre-boarding in California to splashdown in the Philippines. Achieving a 37-minute trans-Pacific crossing is a complex optimization problem. It balances extreme human factors, heavy offshore logistics, and precise unit economics. At T-minus 45 minutes, operations begin on a launch platform positioned 15 to 20 kilometers off the coast of Los Angeles. This specific offshore distance is mandatory. A super heavy booster generates severe acoustic disruption and requires expansive hazard clearance zones that a dense urban center cannot safely absorb. Passenger boarding logistics rely on a specialized support fleet. High-speed marine ferries transport ticketed passengers from metropolitan executive terminals directly to the platform lounge. The financial mandate dictating who gets on those ferries is strict. To clear its massive operational overhead, a single flight must generate a minimum of $3.5 to $4.5 million in gross revenue. This payload cross-section illustrates the heavily stratified pricing model. The top executive tier, at $10,000 to $15,000 per seat, targets C-suite executives needing time compression. The standard commercial tier sits below, at $2,500 to $5,000. The lowest volume houses bulk cargo at $8,000 to $12,000 per ton. This bay exclusively handles time-critical assets. The primary targets are urgent medical supplies, high-value microelectronics, and semiconductor wafers routing between North America and Southeast Asia. Once passengers board, the environment shifts. Unlike commercial air travel, suborbital transit subjects the human body to an intense physiological profile. Pre-flight protocols require mandatory medical screening. Every passenger must clear cardiovascular and pulmonary evaluations, backed by baseline ECG testing, to ensure tolerance for a high-G environment. Physical preparation extends to a mandatory one-day simulator briefing. Here, passengers learn anti-G straining maneuvers, or AGSM, to manage blood flow during launch. Standard civilian clothing is replaced by specialized flight attire. Passengers wear pressurized suits equipped with integrated biometrics tracking and emergency oxygen supply systems. Between the $15,000 ticket prices and the intense physical demands, suborbital transit functions as a highly specialized logistics and executive transport solution. It is a distinct operational category, separate from mass-market commercial aviation. At T0, the super heavy booster ignites, generating the immense vertical thrust required to clear the offshore pad and push into the atmosphere. Before tracking the ascent, we can analyze this operational cost breakdown. Fueling consumes 65% of the operating budget. The remaining capital goes to 20% vehicle amortization, covering heat shields and engines, along with 15% for support fleets and insurance. Supplying that volume of subcooled liquid methane and liquid oxygen requires automated ship-to-ship transfer systems, pumping directly into the floating pad. Returning to the flight timeline, at T+2 minutes and 24 seconds, the vehicle reaches the critical hot staging separation event. Post-separation, the Super Heavy booster flips and immediately executes a boost back burn, targeting a precise landing back at the offshore launch site. Inside the passenger cabin, the physical reality of the ascent sets in. During this sustained acceleration, passengers manage continuous physical loads of 3 to 4 Gs. Maintaining consciousness relies on proper positioning within the acceleration harness and the active execution of the anti-G straining maneuvers practiced in the simulator. The physical strain peaks just before T plus 8 minutes and 11 seconds at Starship main engine cutoff, or MECO. The engines silence and the vehicle enters its coast phase. At the apex of the suborbital arc, passengers experience a brief period of microgravity. The nearly $1 million cryogenic fuel burn and the 4G physical loads dictate the operational limits of suborbital transit. It is an exercise in extreme energy management. At T plus 28 minutes, the vehicle initiates atmospheric re-entry over the Western Pacific Corridor, slamming into the atmosphere and generating extreme kinetic friction. Over the Philippine Sea approach, peak atmospheric heating on the vehicle's underside exceeds 1400 degrees Celsius. Surviving this thermal load relies on next-generation reusable thermal protection tiles. The materials are designed to endure the friction without requiring total replacement between rotations. Operating at point-to-point suborbital speeds demands absolute redundancy across all flight-critical systems. Primary abort modes incorporate an automated launch escape system. If telemetry sensors detect an anomaly, the software triggers protective parameters instantly. The transoceanic trajectory features built-in abort landing zones, utilizing designated splashdown support vessels stationed at specific intervals across the Central Pacific. Assuming a nominal flight, the final descent profile relies on redundant inertial navigation, backed by real-time satellite telemetry, steering the vehicle without local ground infrastructure. During a Mach 20 descent, human reaction times are a liability. Safety depends entirely on closed-loop autonomous software calculating the precise coordinates of the offshore landing ring. The vehicle executes a vertical retro-thrust landing onto the floating platform in the Davao Gulf. Total active flight time, 37 minutes. With the journey complete, this tests the initial revenue thresholds against final unit economics. Assuming a conservative average yield of $4,500 per seat across a high-density configuration and full cargo bay, a single flight pulls in between $3.5 and $4.5 million. That gross revenue comfortably clears the $1.3 million operating overhead, providing the necessary margins to make the U.S. to Philippines route commercially viable. The macroeconomic impact of that math positions Davao City as a premier international suborbital terminal. It directly links Mindanao's industrial sectors to North American markets. Goods and executives completely bypass congested, traditional Asian layover hubs like Manila, Tokyo, or Singapore. Trans-Pacific logistics lag collapses to under an hour, accelerating the delivery of medical cargo, microelectronics, and executive transit straight into a booming economic hub. The transit is entirely frictionless, completely ignoring conventional air traffic corridors and unpredictable jet stream delays. The components of this architecture are permanently locked together. The extreme physical parameters demand the offshore infrastructure, and that expensive infrastructure demands the high-yield economic model. Project Apollo-Mindanao proves the future of intercontinental transit involves leaving the atmosphere entirely. It requires integrating extreme aerospace engineering with high-velocity global economics.